So like I said, we are going to look basically something that is called genetic algorithm, yeah, to explore the design point, and this could be the goals, yeah. And for sustainability, we want to minimize energy dissipation, okay. But before we go to that, I wanted to introduce something that typically happens in a car. So before we look this one, let me try to explain something like how the car operations are defined into different modes, yeah. So it's like when you want to drive your car, first you go near it, right, you unlock it. So that's like one of the mode of the car, let's say mode 1. You unlock, few electronic control units start doing something, which means those runables, we said 18, right, that's very toy car, yeah. So some of the activities starts happening in some of the electronic control units, which means some runables starts running. When you go in the car and do maybe not start the engine but turn the ignition on, then there are more electronic control units doing more tasks. It could also be it's the same task or same runnable, but they are running more frequently. Previously they were maybe running once in every second, but now they may run like 50 times 1 second. So their period changes, yeah. And then when you start the engine, that's called like cranking, then you like more runables run in different electronic control units. Again, it could be the frequency of runables may change. Again, when you like start driving, then the state again changes, and in driving as well, it could be you are driving at low speed, that's one mode. Then if you are driving at high speed, that's another mode. In all these modes, there are runables running in different electronic control units, yeah, okay. So that's kind of a way to define the state of a car, okay. So this is another way to define the state. I think this one is defined by Infineon, yeah. So they are kind of major software developers for automotives. So they say there could be kind of power down mode, that means nothing is happening. This power up mode, like car is running, is stalled, like you were driving but all of a sudden you stopped it, yeah. Cranking, we have seen it. Idle, like maybe you are waiting at the traffic junction, yeah, and you are driving, okay. And then there is some wait, okay. So like I said, runables behave differently depending on the state. So in some state they may run more frequently, in another state they may run less frequently. So now you can see there is a lot of states, right, and if you are driving your car, if you are changing from one to another, it might be so much changes, yeah. So that means you need to switch from one mapping to another. So runables need to be distributed always in a different way. So some companies propose like we can cluster some of the modes, yeah. So it's like power up is there, and some modes can be clustered into cluster 2 and some in cluster 1. The reason is then you don't need that much switching, yeah. And another is the modes in one cluster, they are also more or less similar, yeah. So it's like if you are, let's say, driving from 0 to 20 or from 20 to 40, there is no need for two modes, yeah. They all can be combined because behavior is more or less the same, okay. So like I said, this is to avoid this context switching a lot, yeah. And some of the neighboring modes, like I said, they are quite similar, so no need to have separate modes. Now we will see like how we can apply genetic algorithm for one of the modes, okay. So anyone aware of the genetic algorithm? Have you used, have you heard? Some of it, yeah, okay, good. So maybe I will just quickly brief, yeah. So what do? You take your application model, you take your platform architecture, yeah. Application model means like how many tasks it has. So you saw we have 18 runables, yeah. And platform architecture, like what is the architecture on which those 18 runables are going to run, okay. And with those application and platform, you create some initial population, which means let's say maybe 10 mappings. Yeah, those 18 runnables, if it is like on a 4 core, there are so many possibilities to map. Yeah, maybe all on 1, distributing on 2, distributing on 3, this way. You basically generate some initial population. It's like initial design point, and then you evaluate all of them. Yeah, so evaluation can again mean like what you are evaluating, maybe energy consumptions or their timing. Yeah, and then from those initial populations you do some selections. Yeah, to choose maybe 2 of them and do some operations like crossover is one popular operation, another is mutation. Yeah, so you can see in crossover it's just like something, one particular kind of mapping, or like one task is moved from one place to another. Yeah, in mutation it's like more. Yeah, you can read more details there, and then you get a kind of new design. Okay, so then this one is called offspring population. After that, what you do, you take those initial ones and then the new ones that you have produced and make a combined population. Okay, and then from these combined you choose the elite groups, that means the one that are giving the best result. Yeah, so it's like, let's say initially you started with 10, here maybe you got one more, then out of these you just choose 10. Yeah, so basically discard the one that is not the best, and then these the best ones or elite ones you make the initial population. Again choose some, do these things, you keep doing. Yeah, and after some time you will find like these ones are the best ones. Yeah, so this is how you can say genetic algorithm is applied. Okay, and here we will look like how this can be done for power up mode. Okay, so I hope the concept is clear. Yeah, it's and this can be applied forever. Yeah, unless you have explored everything. That is why when you are applying genetic algorithm, there is something like number of iterations that you want to do. Maybe you want to stop after 100 iterations. Yeah, it's like training epochs. Yeah, how much time do you want to do? Okay, so like I said, in the fitness you can set some criteria. Yeah, so you want to reduce the energy consumption because of sustainability goals, and you can put huge penalties for deadline miss because it is safety critical system. So if you are doing that, your basically the elite group will be trying to choose the population that will try to meet those goals. Okay, now in the genetic algorithm there is something called genes, right? That's how the name has come. So don't look the top one, we forget the top one. So you know we have like 18 runnables, right? So let's say these are the tasks, yeah, or processes, and that need to be mapped on the electronic control units. Yeah, let's say these are the electronic control units. Yeah, so these runnables has to be mapped on it. So this now has to be the platform, and the application has to be represented into some gene format. Yeah, so what we do for each runnable, basically we take one gene. Yeah, so let's say if we have n runnable, we take n genes. Okay, and how many cores we have, we take that many extra genes as well. So if it is like x by y, so we take x into y genes for the cores. We are doing these things because here with these ones we are going to explore mapping, and with this one we are going to kind of find out the best power operating mode or best DVFS point. How this will be done? So like in this one, basically you can put like runnable 1, yeah, and if sorry, you don't, so kind of this is each representing runnable, right? So here if you have to find the mapping, you have to find out where the runnable 1 is going to be mapped, yeah, where runnable 2. So inside each of these you can put the core, which core on which core number it is going. Yeah, you can say this pi 1y. Yeah, in the second one also you can say pi 1y, which means runnable 1 is going on 2 cores. Yeah. So this is like how you can define the mapping, and in this one, like this is all different cores, so you can decide what are the power modes. Okay. So you can see just with combining some genes, you can define the mapping and you can define the operating voltage frequency as well. So now you remember in the previous slide, we start with some initial population, right? So this is one of the population. Similarly, you can generate more, maybe 10 of them, and then apply that process and keep repeating the process. After certain point, you will get some points, or you can choose the best gene that will say, okay, what is the mapping? Yeah. So that means what is the core number inside each of the runnable genes and what is the voltage and frequency, and then you can choose the best design point. Okay. So this is how it can be applied. Okay. And we applied this for automotive car. I think we, in the genetic algorithm, we do like hundreds of iterations. Yeah. And then we stop, because that already takes like 7-8 hours to do it. So that's why we have to stop. Okay, now I have a question. Let's go to that interface. Not yet. Not yet. Oh, have we gone back? This one. Okay, some of you already answered. Okay, it's always good to see responses at both the places. Yeah. So will you always get optimal design point when using genetic algorithm? So optimal means the best. Yeah. There cannot be anything better than that. Yeah. Yeah. So if you want to get the optimal, there are ways. One is exhaustive, right? You explore all the points and then just choose the best. But having 18 runnables, maybe 9 cores, it's going to take so much time. Yeah, it won't be possible to do exhaustive search. So there is a possibility you will not get the optimal point. You will get the best or the most efficient, but you may not get the optimal design point. Yeah. So if you are working into this kind of field, like exploring the design space, there's always a question like how far you are from the optimal, or some people say like oracle solution. That's like somehow you get the best, like exhaustive search. Yeah.
Isn't the most efficient the optimal one?
Yeah, it's most efficient. No. So if you're doing some explorations, right, that will give you something that is best, but that may not be optimal. I mean, you might have missed optimal in exploring the whole space. So optimal is something, there's nothing better than that.
Better in terms of efficiency, right? Isn't efficiency what we are going for here?
Yeah. It's efficiency, like let's say the one we want should have minimum energy consumption. Yeah. So it could be you can find, but it's possible you will miss it as well. Yeah. Because you started with some population, right? And then you are going further. So it's like humans, right? Because this genetic algorithm is like human reproduction system. Yeah. So I mean, it can be always better. Yeah. So the thing is, you may find, you may not find. Yeah. Okay. But it's kind of just a chance. So it cannot be proven like you have reached the optimal design point. Yeah. That is why if you apply genetic algorithm, any like kind of pruning, everybody will ask you how far you are from the best or the optimal. But in some situations you can't really find the optimal. Yeah. So in that case you just have to say something in comparison to what research has already been done. You say, okay, I can perform my search in less time, and the solution that I get, it has better energy consumption or kind of lower energy consumption in comparison to existing approach. Yeah. Okay. So yeah, so you may not get always optimal design points. Yeah. So the thing is, if you have like maybe less number of cores, yeah, your gene size is small, that means less runables, less cores, it might be possible. Let it run for maybe a couple of days, then you may find the best, the optimal, but not if there is huge possibility. Okay. So yeah, if you get a question like that say no. Yeah, it always is stuck. So when I use this interface, let's see. Okay, all right. So I'm not putting some results because I wanted to cover some more things that you may find interesting, but these are listed in this paper. Yeah. So also this work, now I'm not focusing at the moment. I'm trying to apply now genetic algorithm in some other domain, but this was for automotive domain, and we got the paper published, but others we have not published yet, so I have not covered. Yeah, but same can be applied other places as well. Okay. So now let's look the partitioning. Yeah, we covered another aspect, partitioning. Yeah. So in a specific we are going to look the partitioning between CPU and GPU. Yeah. So if you are partitioning, it's again design space exploration. Yeah, it's just to find out what fraction of workload you want to put on CPU and what fraction you want to put on the GPU. Okay. So this slide you have already seen. Yeah, this is just one example partition, like 40% of the workload on the CPU and 60% on the GPU. Yeah, but there could be other possibilities as well, right? So in one of the experiments, so what we did, basically we took 4 applications. This is like SYR2K, SYRK, correlation and covariance. Okay. So I think these are from Parsec benchmark or its modified version for CPU GPU workload, and we measured execution time, that is shown by bars, and the energy consumption, okay, that is shown by lines. And here on the x-axis it is about the fraction of workload on CPU cores. So it's basically defining how much will be on the CPU, how much will be on the GPU. So if you say fraction of workload on CPU cores is 0, that means everything is on the GPU. Yeah. If fraction of workload on CPU core is 1, that means everything is on the CPU, nothing is on the GPU. Yeah. If you come like 1/2, that means half of the workload is on the CPU, half is on the GPU. Yeah. So with this you can see different partitioning is giving you different timing results and different energy results, right? And with this kind of graph, you can also see some applications are running well on the CPU, right? So you can see this red bar, right? That is correlation. If the fraction of workload on CPU is 1, yeah, like everything is on the CPU. So the timing is like, I think if you go here, like maybe 50 seconds, yeah, or 55 seconds. But if everything is on the GPU, that takes more than 120 seconds. So it could be there are some applications, they are not the best on the GPU, they might be best on the CPU. Okay, so this is the first point, yeah. But if you look in general, the timing is somewhere best here, right, lower, and even the energy is somewhere kind of lower in the middle. That means it's always good to partition, but you need to find out which one you choose. Yeah. So I think if you want to kind of take care for both timing and energy, so you can think of, you want least time, you want least energy, right? You can multiply these two factors, and the one that the partition that give you the least of the value, when you multiply both time and energy, you can choose that. Yeah. But if your energy is more important, you just should look that. Yeah. If your timing is more important, you can look that. Again, think like we have done partitioning not at very high granularity. Yeah. This is like only 8 of them. Yeah. You can think of even 100 ways. Yeah. So it's like 1/8, then like that's the smallest. Yeah. But you can think of the whole workload, maybe 16 partitions. Yeah. Maybe even more, 32 partitions. Then this design space can be even huge. Yeah. So this is how you can explore the kind of partitioning results. Okay. So that's all about design time optimizations. Yeah. So here it's like if you know the workload, you know the platform, you can find out what could be the best mapping, what could be the best DVFS points, and what could be the best partitions. Because you have a lot of time to explore, you can do it. Okay. Now the next thing I said, the whole management, resource management can be also in the form of runtime optimizations. So this is the kind of situations where things are changing a lot. Yeah. Like I said, in our smartphone, different applications are running at different times. So then design runtime is better typically. Okay. How this is done? So in all the device, we typically have this 3-layered architecture. Yeah. So at the bottom there is a hardware. Yeah. Again, we have seen some hardwares. These are like hardware resources, maybe some CPUs, some GPUs, and they also support some voltage frequency labels. Yeah. And these hardwares also have something called performance monitoring counters. They have different registers. Yeah. Different things are logged into that. You read them and then you basically find out, yeah, like how many instructions per second are being executed. Or sometimes there are sensors into that. You can get the power, you can get the temperature, all those kind of things. Yeah. And the top you have applications, right? And these applications again can be multi-threaded. So like there are many processes into one application. And they might also have some requirements. Yeah, like you don't want to take too much time to run an application. Yeah, or you don't want to waste a lot of energy for an application. So these applications have to go on the hardware. But typically then in the middle we have something called like runtime management layer. Yeah. So this is typically in the operating system. There is a module that decides how things are going to be mapped or where things are going to be mapped and how this will be running. Okay. And this module that decides this kind of arrangement, it's called like operating system scheduler, yeah, or power governor. So there are two entities. Scheduler is basically deciding thread to core mapping, so where things are mapped, and governor is going to decide at what voltage and frequency the cores will be running. Okay. So now you can see again, this has a complex job, yeah, because there are so many resources for each application. So now when it's performing its job, it has to address so many challenges. Yeah. Coming to sustainability point of view, if it could be like if one of the, I mean, so it's like there are many cores that the application may need, right? But if lots of applications are running, it's difficult to find out which one to allocate to which one, right? And here some cores may heat up excessively, right? Maybe one core is being used a lot and it may fail. So we have to find out how to keep them cool, yeah, or how to work around it, okay, to make the chip last longer, yeah. So this one we have covered. Again, if there is one application or two applications, it's not that difficult, right? Because there are so many of them running at the same time, so the job becomes difficult, okay. Again, you remember, like we said, that these architectures these days are becoming more and more heterogeneous, right? There is many types of CPUs and GPUs as well. So that makes this kind of scheduling or governing decision even more difficult. Yeah. So these are the kind of research questions that this particular component has to address. Okay. And if we look like from sustainability point of view, we want to care for energy and reliability of the system. Yeah. So reliability means it's operating in a reliable way, and also it should last for a long time. Okay. So these are the two metrics that we can look. Okay. Now these approaches, I mean, they are called runtime management, and some people refer it at like dynamic resource allocation. So dynamic means runtime, yeah, and some people also refer like adaptive, yeah. So these can be categorized into two main parts. One can be for like hard real-time system. So you know these are safety critical systems, yeah, where timing is very important, like in aeroplanes, in cars, yeah, some other places. Another is called like soft real time or best effort systems. So that are like video streaming is an example for it, yeah. It's like if your TV becomes slow, or if you're watching something it becomes slow, it's not going to cause any kind of consequences, yeah. So you can basically cope with the degradation in the performance. So that is like soft real time. So there is a timing requirement, yeah, like we want the video to be smooth, but if it is not, it's fine, yeah. So that is why it's called like soft real time. You should meet, but if you miss, there is no consequences for it. Here there are two categories. I think we don't have time to look into that. In soft real time, there are again lots of categories: market inspired, bio inspired, non-guaranteed admission control, and congestion avoiding. Okay. So out of these, I think I will cover these two: bio inspired and congestion avoiding briefly. But if you want to look all of them in details, even the comparison results, that is in this paper, yeah. Or I think this was a tutorial or something. So it was presented in that tutorial as well, okay. So like I said, congestion avoiding is one of the I wanted to cover, right. So let's say if your application is in this format, right. I am saying this as a task graph, but you can imagine this is just a multi-threaded application, yeah, any application. And if you have this kind of architecture, what you will try to do, you will apply best effort to map computations and communications, yeah. So you can see T1 to T4, they are mapped in some way, yeah, and what this best effort should try to do. So it should try to avoid congestion, yeah, and congestion happens when things start talking, right. So it should try to kind of as less congestion as possible. So how you can do that? So congestion doesn't mean like only when things are communicating, because if you put lot of tasks on one place, then also it is a congestion, right. So to minimize that, you can try to homogeneously distribute loads of the tasks, yeah. So try to use as much as resources possible, yeah. And for links, communication overhead should be minimized. So it should not be like you put T1 here and put T2 here, then it has to talk a lot, right. So they should be put close to each other. But you can say if I want to minimize my communication overhead, I may put all of them onto one, right. Then it's very fast communication, but then the load is too much, right. So we need to find a balance, yeah. So there are some approaches kind of finding out how much workload this one will impose, how much this one will impose, how much this one will impose, how much this one will impose. And then you can find the kind of right balance by distributing it into a couple of sets and then put that onto the course. And when you are putting, you can think of the reducing the communications, yeah. Don't put the ones far away that they need to communicate, okay. So this is congestion avoiding, okay. And the same can happen everywhere, yeah, like in data centers, in servers, it applies everywhere, okay. Okay, maybe I have already given you the answer to this question, but the question is, will it be better to map all tasks and edges to one core to reduce congestion in the cores and links? So you said previously we mapped this way, right? Now I am saying, if you really want to reduce the congestion, why not map all the tasks onto one core? So do you think it will be better to do that? No? Okay, let me hear your thought on those interface. Not yet. If you can try to give your answer like yes with the reason and no with a reason. I think we can also speak. Typically I am keeping this because we have sometimes some people online. Yeah, I think we don't have many, but sometimes we have. Yeah. Also, if you prefer typing and not speaking, it helps. Hope you can see the interface. Yeah. Yeah, I see it. Good. So no, it will cause overloading. Yeah. No, because the other cores will be idle and there will be no use of them. No, as the trade-off is not worth it. Inter-core communication latency is much lower compared to the time you will lose by putting all the computation in one core. Okay. I think most of you are getting it. Yeah. So remember, like, if you could put everything on one core, there was no point of multi-core systems. Yeah. So multi-core came in because then you can distribute and do the things faster. Yeah. So this is similar to like long back we used to get this what is that we cook on food on, like the gas, right, with only one burner. Yeah, people thought, okay, making the burner as powerful as possible to cook fast, but then you have to cook so many things, there's so many workload. Yeah, and then people thought, okay, let's have 2, 3, 4, 5 burners. Yeah, and I imagine like previously there was 1, then 2, now I see 4 and 5. So it's like more and more, so you can perform things in parallel. Yeah, all of them are on, so you finish in much less time. Okay. So same here, if you put everything on one, there is no congestion in the link. Yeah, because they can talk through the shared memory on the same core, but it will take long time to execute because that core is going to kind of do some kind of ordering of the tasks. Yeah, so it will take more time. Okay. So not worth it. Yeah. So both load on the cores and load on the links should be kind of minimized or balanced. Yeah. We have not talked much about links, but it could be also sometimes like maybe this link is being used too much. Yeah. Maybe there are like lots of communications, lots of tasks want to talk. So then in that case it might not be better to put T1, T2 here, maybe put T1 here, T2 here. So that one can talk independently here and this one can talk independently here. Okay. So these kind of things needs to be looked. Okay. Right. Okay, this one takes time to move to the next slide. Okay. Okay, another thing I said we will look is this bio-inspired approach. Yeah, reinforcement learning. Again, anybody knows this reinforcement learning? So this can also be used to do kind of some resource management to again reduce the power consumption. So we reduce the energy bills and related costs. Okay. So what typically happens in kind of this reinforcement learning, you have some kind of environment. Yeah, let's say earth, and also you have an agent. Yeah. So this agent basically observes the environment. So in what state this environment is. So that's the first step. It observes the current system state, and based on the state it selects an action, and that action will be applied to that environment. Yeah, and if you are doing that, basically the state will be changed. Yeah, and if the state is changed, it will lead to some kind of something good or something bad. Yeah, so if it leads to something bad, basically then it can kind of observe the state again, then it may select different action. Yeah, unless it gets something that is more useful. So this is how you can say the reinforcement learning works. So it keeps trying unless it keeps finding better you can say design point or better system state in which it wants it to be. Yeah. So now similar concept people have applied onto this when you want to run the workload onto the processors. Okay. So something like this. So you have the hardware like your this environment, yeah, and you have your learning based algorithm that's like basically a brain agent, yeah, that's like in the scheduler of the processor. So here from the hardware you can get some feedback, yeah, like I said there are some sensors, you can get temperature, power, and you can go get some other values from some registers. It's called like performance monitoring counters, yeah, like how many instructions per second are happening, what is the CPU cycle, or what is the utilization of the hardware, yeah. Utilization you can always see in the CPU, right. So based on the state basically it defines some action. Action could be, if this is a task graph, changing maybe it to from core 1, core 2 to maybe core 3 and core 4, yeah, and then looking like with the changed state whether your performance or energy has been better or not, yeah. If not, again kind of apply some different action, yeah. So it keeps doing this unless it finds a point it is happy with it, like okay, I'm getting better results in terms of energy or power. Okay. Now you can see like this is like a kind of is trying to optimize over the time, but if your workload change is very dynamic, it might not give you the best results kind of maybe after until 1 hour or something, yeah. And if you again something changes very drastically, it has to again learn the best thing to do, right. So in some situations it might be good, but it again expects the workload not to keep changing a lot. Okay. Okay, again a question. So do you think there is any problem with reinforcement learning approach? Okay, let's go that one. I think it looks very fancy, right? Feels like it can give you the best result in all the situations, even people have applied. But like I told you previously, in our smartphone there is no reinforcement learning basically to manage the processor cores for the applications we run. Yeah, training time. So basically you are kind of finding the point when you are satisfied, it can be long, yeah. Yeah, it kind of lacks the feedback mechanism. It's just kind of trial. It's trying, yeah. May take more overhead to find the optimal state. That's correct. So you see, you are putting this extra algorithm, right? It has overhead. You are paying for energy cost for it to run. What if it doesn't find anything good after some time? Yeah, even if it finds, maybe that application is going to run maybe 1 hour, right? But it finds the best point maybe just at 50 minutes. So then only for 10 minutes it's running in the best way. But this 50-minute, this reinforcement learning algorithm is extra software, yeah, extra overhead. So we have to kind of find out in what situations it can be good. Okay. So I would say there are some other problems with it. It's not very scalable. So imagine like you have lots of cores, yeah, and if there are a lot of cores, and it could also be the cores are now heterogeneous, yeah. So then it has to basically keep trying for a long time to really find the best solution. Okay. So it's kind of not very scalable. So it again wants like a bit of more static situations, yeah. For Earth example we gave might be good, yeah, because there are global warmings happening, so things little bit are changing. So you can apply some actions like you can plant trees, Those are the axons, yeah, and then observe what has happened to the planet. It's slow process, slow moving, but in our systems things are moving very fast, yeah. So not the best in kind of very dynamic situations where there are huge number of possibilities, okay, yeah. I think you can search on my web page. I'm not going to in the details of like how we have exactly applied into some kind of real systems. This one we applied on a smartphone. It's not the best in comparison to what already exists, yeah. So at the moment in a smartphone, most of this is based on utilization. So like what is the utilization of different cores? Based on that, the workload is switched from one place to another. Because utilization is just one entity, and that gives very right kind of measure of the workload, yeah. So it basically it still gives better results, okay. Okay. What's happening? Just give me a second. Nothing moving. This one can help. Okay. Okay, now it's working. So now I want to introduce some work. It's again is on intelligent computing. Yeah, again, intelligent computing means finding the mapping in the best way and finding the voltage frequency points or finding the partition, yeah, so that your energy consumption can be minimum, okay. So first we will look for like a small scale system. A small scale, I mean this could be simply the smartphone, yeah, and then we are going to look for like a bit large scale system like on a server, and then how we can do the same onto the data center scale, okay. So I will just try to brief these works, okay, so you can get the idea. So one of the work again is by a PhD student who has proposed is like called adaptive DVFS. Means like over the time, depending upon the situation, you keep changing the voltage and frequency so that you take basically less power, yeah, and at the same time try to meet the expectation of the smartphone users, okay. So these are the same blocks, yeah, you can see. Now in the middle where we said there should be a component that kind of maps this on the hardware, he proposed his own approach. It's called like QARM, yeah. I think I forgot the full form. It's like quality aware something, yeah, quality assurance, something like that, resource management, yeah. So how it works? So I mean this is just with respect to smartphone. So first it predicts something called like TP. So it's like the time when you are going to plug in your smartphone for charging, okay, and then like how much energy you need for that. So ED is energy demand and TP is the time when you want to plug in. So this research was done only with the aim, like we all are here, right? It might be you will go to your hostel or room maybe at 5 or something. So you can kind of, this is prediction is you will plug in your phone at 5 p.m. yeah, but you can check like how what is the battery level of your smartphone, yeah. From there you can think of like whether it's enough or not and to last until 5, right. It depends what you're going to do with it. If you're going to use lot of applications, it might not last for a long time, yeah. Based on like what you're going to do in the next couple of hours, it predicts the energy demand, like how much energy will be needed until you plug in your smartphone based on your behavior, yeah. So some people use the phone a lot in the afternoon, so that kind of behavior is taken into account. So when you are going to plug in and what kind of how much energy is demanded or needed until that point, okay. So that is predicted and this keeps happening after certain time, yeah. You keep predicting because things keep changing, and then you do some update of the model. It's with respect to energy remaining and energy demand. So at first this update doesn't happen, yeah, it's like after some time, yeah. So let's forget this one. So you can come to here, yeah. So you know you at 5 p.m. you will plug in your smartphone to charge and you can predict how much energy you need, yeah. And you can calculate this delta factor, that is like energy remaining divided by energy demand, yeah. So if your phone is charged a lot, like 100%, you have a lot of energy until 5 p.m., right? But let's say if it's only 20%, right, then energy remaining is not that much, yeah. But it could be because you are going to do lots of things into your phone, your energy demand is too much, yeah. That means it's not easy to last the phone battery until 5 p.m. Okay. So this delta factor, it says if it's less than 1, which means demand is much more than the remaining energy, right? You need much more than what is left. So what you can do here, then he kind of finds out the frequency at which you can reduce the phone to run. And this is kind of done again with some trials. So it finds the lower frequency so that the phone is not taking a lot of battery, yeah. So you can imagine what could happen. It's going to impact some performance, yeah. Might be your applications are slow or you are not getting the best user experience, but it's trying to ensure your phone battery will last until 5 p.m. Okay. But for some other of you, it could be your energy remaining is a lot, yeah. And then demand is not that much, maybe your battery is 100% charge. So you can run at some higher frequency, so your kind of quality of experience is not compromised, okay. And this keeps happening at regular interval. So that student set up like 1 minute, 2 minutes, 5 minutes and keep doing this with the aim like you don't need, you can keep running your application until you go and plug in, okay. So you can see this is kind of energy kind of management. So it can be applied other places as well, but that student has applied in smartphones. So something like we discussed, yeah, in data centers sometimes there are renewable energy available, yeah, and that is not forever, yeah. So you can think like that renewable energy is maybe until 5 p.m. or something. So how you can maximize things within that limit, okay. So something like that can be thought through, okay. Again some evaluation results. So I will tell like this one, like there is something called like default method that is in the smartphone. This is in all the smartphone at the moment. That is running. We took that method and there is another method called like power save. So power save, like it says, right, you want to always run at the lowest frequency, yeah. So in the phone, if you can open the operating system, you can change the default. So we did change. And another one is like quality aware approach, yeah. That means you always want the highest quality, which means you always want to run at the highest frequency, yeah. And this is another approach existing, proposed in the literature. It's called like user and battery aware resource management, okay. So in comparison to these, if we look our approach, basically we took the energy demand into account, yeah, like until the plug-in happens for charging, and we also take the user behavior, okay. So it's kind of a bit more learning with respect to the user, and we will see how the results are when we compare all of these. So this is the one set of result. So what we did actually, we took the phone and we started with different initial battery level, yeah. So we charge the battery full, we start with it. You are at 90%, you start with it. You are at 80%, you start the day with it, and 70% you start the day with it, yeah. So and the phones you have different people are going to use in different way, right. So we are measuring active time, yeah. So like until what time you can be active, yeah. Another thing we looked is final battery level, yeah. So you can see like if you are starting maybe at 90% initially, at the end of the day with different approaches you will still be left with some battery, right. But if you are starting with like 60%, like I said, if you started morning with 60%, by 5 p.m. you will have no battery level left. Okay. And how much time you can be active, you can see, yeah. So if you started with 60, you cannot be active after this, yeah. Maybe by 3 or 4 p.m. your battery is gone. Okay. So when looking these approaches, you can see power save first, yeah. Power save is something is always going to run everything at the lowest power. So you expect this one will be the best in terms of lasting for the whole day, right. So you can see this one, power save, the star one, the active time for it is the longest, yeah. Okay. And for this the same will happen with the what is the final battery level left. Okay. But if you go the quite opposite approach that cares only for the performance, yeah, that will always run at the highest frequency. So in that one you will see the active time will be the least, right. And again the final battery level will be quite low. And other approaches are somewhere in the middle, and same our approach is somewhere in the middle. You can see here quorum. So but when we look like we try to combine all the metrics, yeah, like we want to be active, we want to take minimum energy consumption, then our approach sits in the middle and performs better than existing approaches. Okay. So these are some quality of experience results for different approaches, yeah. So you can see how much they are getting with different initial battery labels, and more details are in this paper, yeah. Okay.
This approach is like kind of balanced.
Yeah. So the only main aim was, this student is from Nigeria. So in Nigeria people worry more about battery level or everything, these things. Even in here, right, you leave your room, you always check your battery level, right. You always want to make sure by the time I come back and plug in, my battery should last, yeah. But sometimes when you go out, you are going to check emails, yeah, you are going to call someone. So you have a behavior, you also can't control it. So you can keep doing it, but you will not get the best performance, yeah. So even if you are watching some video or something, maybe with this approach he has developed like it will reduce the brightness level automatically, just to make sure by the time you come back to the plug-in, you basically have the battery, yeah. And it's also one of the most worrying factor for human, yeah. We always worry like how much is our battery level, even if sometimes it is 80%, we fear like, okay, I do not know whether I will come back with some battery left or not, yeah. Okay.
It is kind of dependable on the timetable now. When you will charge your phone, it will get the time key is time to charge karte.
Yeah, that's true. Also sometimes people are in like mountains, in travel, there's no facility. If you can have this kind of technology, it can ensure, like just say I want my battery to last for 3 days, then it will not allow you to run some applications that are very kind of power hungry, or the ones you are running you will be penalized in performance little bit, yeah. Okay. So that was for like a small scale system. So how that kind of intelligent computing can be done for servers, yeah. So server is again like a big chip that has many cores, right. So what typically you do here, you can have lot of applications that can arrive at different times, right. And then you basically allocate those applications onto the server, basically on the cores, and you try to optimize something, right. So for the servers, one of the aim is throughput, like you want to run as many applications as possible within a certain time, and you also want to optimize energy consumption, yeah. So that the energy bills can be lower, okay. Similarly, for data centers, I think we have seen this, so we can be quick. So you can have the data center environment, you can have different users across the globe, and they can submit their job, and you can try to optimize value and energy consumption. Like I said, value is the money, the profit for the data centers. Okay. So these are the two things basically I would say for sustainability, but we also saw there could be throughput optimization. Yeah, there could be some kind of security optimizations as well. So if it's about security, there could be kind of some secure zone, non-secure zone. Yeah, if it's kind of something from the defense sector or something, you put things in the secure domain, secure kind of nodes. Okay. Okay. So now we will look one of the approach that was developed in my group. We call it monitoring enabled adaptation in data centers. Okay. So first let's look, there is no adaptation. So adaptation means you start on one core, but then you switch on another core. So but this one is without adaptation, so non-adaptive. Yeah. So let's say you started with something like this, yeah, and you had 3 cores. So this is just an example. And when this task arrives or job arrives, these 2 are busy, yeah. So it will allocate on core 3, and even if they are free, it will keep executing it on the same core, yeah. So from this we learned like there is opportunity when this one becomes free, we can try to shift the workload here, yeah, or distribute. When this one free, we can distribute on 3. But in order to do that, you need some mechanisms, yeah, some monitoring or check on regular intervals, yeah. So this is what we exactly did. We defined some regular interval, or you can say checkpointing, yeah. So we check here, and this is like maybe 5 minutes interval or 2 minutes interval, and those regular intervals we check like which cores are free, yeah. So for example, here you can see this one is free, so that job is cut into 2 and put on 2 cores. So again at other checkpoint we saw, okay, the third one is also free, so you chop that into 3 parts and distribute. And with this way you can see this one was completed here, but this one is completed here much early, yeah. Another thing we could do, you can see here we are executing the task always on like some different voltages, right? But here we can also think of doing the same, like similar kind of adjustment with the voltage as well, okay. So in summary, you can see this one is completing very late, right? So remember I said there are organizations, if you complete their job fast, you get more money. So this will be basically low value, yeah. Also it will have high energy consumption because it's running for a long time, yeah. So you're paying power for a long time. The one at the bottom, it has early completion, so it will have high value, yeah, and it also has low energy, yeah. And these are some results. So here you can see on the x-axis, this is like number of nodes in a server or in a data center, 2 nodes, 3 nodes, 4 nodes, 5 nodes, 6 nodes, yeah. This is like number of servers, okay. And this is the value, that means money, and this one is the energy, okay. So the bars are basically the value and the lines are the energy. So if you look all these approaches, you will find the one that is this adaptive approach, we name it as like value and energy adaptive optimization, okay. So in that one the value is always highest, yeah. But if you look the energy consumption for it, that's this one, it's not the best, yeah. So the orange one is better, yeah. So it's like we got more in one metric, but we lost in another, yeah. But again, like I said, it depends what is your aim. If you want to combine both of these together, like energy and value together, we found out like then our approach is better, okay. It's getting better results, yeah. So it's like this way you can basically hit both the metric, yeah. Another way to do is, you know, even whatever is energy, right, you can convert that to money, right? Like if this is like how much the data center companies are paying. So that one can be also in kind of value, and then there could be one plot only, yeah. So there are many ways basically to consider it. Again, more details are into this paper, okay. All right, how much time we have left? Like 20 minutes, yeah. I don't know how much slides I have left. Okay, so I will try to be slow, but sometimes if I feel like it's easy, I will try to be fast, yeah, so we can go at the end as well, okay. So another work we did is like, again, regarding sustainability, yeah, reliable distributed inference on edge devices. So let's look like, first of all, why we need distributed inference on edge devices, yeah. So you know, DNN inference is increasingly being executed on edge device, right? Like I told you, there are going to be more and more edge device, and not all the data can be sent to cloud, yeah. So even DNNs are going to run on edge device, yeah. And there's other advantage as well, right? You get latency is lower, yeah. Like if it is autonomous car, you can't run the AI model on the cloud. It has to be running on the car, because it has to take the decision immediately. There are some other advantages as well, yeah. Privacy, so the data is not going out of the device, yeah. So you are secure, more secure with the data, and always on availability. So wherever the data is collected, that kind of system is on, yeah. For cloud, you don't know, maybe it's overloaded already with something. When your task arrives, it cannot do anything. Your task might be put in the queue. Okay, so that's one advantage, and DNNs are also computationally intensive, right? So if you take a very small device, maybe you cannot fit all of it, the whole model, yeah. That is why we try to distribute on edge device, yeah. For example, if there is a big DNN model, maybe it cannot fit on my phone, yeah. So what I can try, like I can try couple of phones, or my phone and laptop, or maybe my TV in the home. I can fit the whole model into these three devices. So chop it and put some fraction here, some fraction there, and some fraction there. That is why this kind of distributed DNN is coming into picture, yeah, because they are still very big and cannot be executed on a single device. Okay. Okay, so now what we proposed is something called like fluid dynamic DNNs that can provide more reliable inference, yeah. This is again related to sustainability. It's like more reliable operations. So before looking at the fluid dynamic DNNs that we proposed, let's look something that already exists, yeah. So something that already exists is one is a static DNN, right? You take the 100% model and train it, and it's ready to be used, yeah. But people also proposed something called like dynamic DNN. So this whole model, what they do, they take that like 25% of the model, they train it, yeah, like this one. So you can see this one is ignored, yeah, the dotted ones. Then they kind of incrementally add another layer, and they train that as well. And then they incrementally add another layer, they train this one. So this is like 75% of the model. And then they add the last layer, train it. So that is like the dynamic DNN, how people have done, yeah. And static is always fixed, yeah, it has all the layers, okay. So even with dynamic, even if there is 50% of the model, it's not going you to give the results like 100%, but it will give some results, yeah. That is how dynamic DNNs came into picture. Also, if this model is too big to fit into one device, you can use only 50% of the model, yeah. You can compromise on the accuracy, but you can fit into the resources that you have available, okay. So what we proposed is called something like fluid dynamic DNNs. So here what we did, we tried to train the upper part, not starting from the left side, rather you can say something in the middle. So this is like upper 25% model we trained, yeah, and then we trained this one as well, okay. So this is like upper 50%, upper 25%. Maybe it's not clear yet what's the advantages, but it will be clear in a bit, okay. So now let's say that whole model has to be distributed on 2 devices, yeah, maybe 2 smartphones, and this is what we already covered. So if it is a static model, yeah, let's say half is going on the one phone, half is going on another phone. If this one fails, the whole system is not going to work, yeah, because you get the output from last couple of layers, yeah. If you look the dynamic, if the whole like static fails, you can still load this model A and B, right, and then you can still get the output. And fluid, you can always get that, yeah. So fluid is like combining this one with some training from the upper part as well. So in this case, dynamic and fluid are going to give you the similar results, yeah. So in fluid is like part is dynamic and then C and D, the upper part is on the faulty node, okay. So you can get the, will get the similar results, okay. So here we are assuming the right device fails, yeah, and there is always like master worker kind of model. So here is like worker is failing, okay. Now if we say the left device fails, the master fails, okay. So you can see the left one is red, okay. So static is not going to give any results, yeah. And if you look the dynamic is also not going to give you any results, yeah, because dynamic is like the training done in an incremental way, okay. So you can see if AB fails, so there is nothing like CD in dynamic DNNs how it is trained. But if you look ours, we kind of have trained the upper part, yeah. So this part is still going to work. So you will still get some results from this, okay. So if you kind of do the training in a kind of some twisted way, even if one of the device fails, you can still try to get the outputs, and this is more reliable, yeah. It makes the system reliable, so you don't need to throw the system out, okay. And these are the some results of throughput and accuracy for these 3 approaches, yeah. And these are a couple of combinations like only worker is working or only master is working or both master and worker are working, okay. Here we have like for the fluid 2 bars, one is for like high throughput, another is for high availability. So just kind of to test 2 different situations, okay. And this paper was published last year in a conference. So again, for more details, you can look into that, yeah. I mean, there are 2 things. One, we don't have time. Other thing is if we go into too much details, we cannot cover other things, yeah, and it can also be very confusing, yeah. Okay, another thing for sustainability. So there is a trend, something called like multi-chiplet systems, okay. So if you look like how the computing started, right, we had this transistor level, yeah. You remember first transistor was discovered, it did something, then there like gate level things were made, then ASICs were made, yeah, just some for some specific purpose. At the moment, like we are at system on chip, whatever we discussed, yeah, the chip in the phone, laptop, everything is system on chip. But in future, it is predicted there will be something called like multi-chiplet system or 3-dimensional integration, okay. I will come to it, what exactly is multi-chiplet system. But before that, I wanted to discuss a kind of, maybe discuss, not ask, why do you think is this trend? So we don't have time for like basically typing. So let me tell you why this things is coming. So when we are kind of producing this monolithic ICs, right, you feel like there was kind of this nanometer, right? They started like long back 90 nanometer, 60 nanometer. At the moment there are 7 nanometer chips, People are trying now 2 nanometer, and there is no way like to go much lower. Yeah, you can't go into picometers. Yeah, because chips start failing, heating more and more heating. So again, there will be no way to go forward. That is why you might have heard people say Moore law has ended. Yeah, you can't pack up more and more transistors. If you can't pack up, the trend is coming like multi-chiplet system. So you take different chips, like one processing element, it can be CPU, it can be GPU, but it is very kind of a small module, and try to integrate that into a kind of big chip, and those can communicate with some mechanisms. There are a lot of ways. One of them is called like interposer system. So some companies have started developing the CPUs, GPUs based on these chiplet models. So very soon I think AMD is going to release one chiplet based chip. Yeah. Okay, this is coming for that reason. Again, you may think why multi-core system came into picture. Yeah, it was like the single processor Pentium. Yeah, Pentium, then P1, P2, P3, P4. Yeah, there was nothing after P4. They're like dual core processor. So again, you could not increase the frequency to very high level because it was getting very heated. So you thought, okay, let me run low frequency but use more number of cores. Now even with that kind of trend, it's ending. So people are thinking it will be like multi-chiplet systems. Okay. I think few things we already have said. They overcome limitations of monolithic dies. Yeah. So if it's monolithic, it's like basically it's again like very low nanometer technologies, making that is very costly and they cannot be scaled. Yeah. So there's end to the nanometer, and if you are doing that, yield is also very less. Yield means like how much many of the chips are good in comparison to whatever is produced. So the process is so complex now, the lot of chips are getting defected. Yeah, cannot be used. And with this multi-chiplet kind of things, it enables heterogeneous integration very easily. Heterogeneous integration is still there. So there are CPU, GPUs, memories all integrated. But this one on top, it allows you to integrate components from different nanometer technology node. So at the moment in the SoC, all CPU, GPU memory is on 1 nanometer technology, yeah? Either everything 35 or 28. But this one will allow, maybe CPU is a 65 nanometer technology, GPU can be a 30 nanometer technology. So those kind of integrations are possible. Okay. And it also facilitated reuse of proven IP blocks. So it's not like you need to keep developing something new. So whatever is existing, if it's already very good, you can just integrate it into the multi-chiplet system. Okay. So there are a couple of other benefits from sustainability point of view as well, right? You can have some specialized chiplets that can reduce energy per computation. Yeah, you can design the system in a way. And these also kind of facilitate modular upgrades. Yeah, it's like one of the chiplet fails, one of the processing element fails, you can always upgrade that. Yeah, this way you can extend the lifetime of the system. Whereas in my phone right now, if my GPU stops working, everything is gone. Yeah, or if my memory stops working, everything is gone. But this one can facilitate easy replacing. Okay. And like I said, faulty chiplets can be replaced easily, and smaller dies improve yield and reduce waste. So with this one, like the die size will not be that big. Yeah, so it's like there is not a lot of waste, you can say. I think this one maybe we can skip. So one of the students actually did some work. He took some applications. He took a kind of chip that has 2 chiplets, and he looked like how the existing approach will map the tasks onto it, and then he developed some communication minimization approach. So again, balancing the computation and communication from the multi-chiplet system point of view. Okay. I think more details are in this paper, so that was just published last year. Okay. Okay, so again, due to time, we are not covering everything, but I also have some work on reliability and aging management. So how to increase the lifetime of electronics, and those things are already talking about it, but there are some more works from the resource management point of view. So when you get time, you can look into those papers. Okay. Okay, so now let's look like what can be the emerging trends from now on. Yeah. So these are my thoughts. You should not take like this is what the world is thinking. Yeah? The world may think in different way, or different people may think in different way. So one of the things I think is there could be increasing type of covert and side channel attacks. So we have seen some, right? The timing, temperature, sound, but there could be other ways coming into picture. Yeah, people can think of different kind of physical properties. So basically, when we have more and more types of these attacks, all of this needs to be considered. Yeah. So as like I said, as an attacker, think what is other extra property that you can use to attack the system. And another thing that we should do, we should have some joint consideration of various attacks. So you can see like some people just consider like maybe temperature side channel attack, and some consider only acoustic or sound, and some are caring only about the password, some are caring about only the malware, some are caring only for the phishing. So nobody is considering everything together. So we should think in a way how we can come up with a solution that considers most of it, or the most promising ones. Yeah. And but you have to also think the solution should not be very heavy. Yeah, it should not take a lot of power and energy. Okay, and this one is actually published in this paper, this figure. Okay, so try to consider as many of them as possible. Again, like if you look again in the whole literature, some people consider sustainability secure, some people consider security separate. Yeah. So there is a need basically to jointly consider these. Okay. In some of the works I demonstrated, I showed you, yeah, like the kind of bit error rate and the power. So it was kind of a joint consideration, but more and more needs to be done. Okay. I think for sustainability, we already have said it's mainly about increasing the lifetime and reducing the energy footprints. Okay. So if we are considering both, basically we need to find the right balance, yeah, between the security and sustainability. And one thing I have missed here, we have not covered, like I told you, yeah, there is a lot of sustainability problems before the time we get the product. Yeah. So a lot has to be done there as well. Yeah. So during the design or manufacturing, lots of sustainability aspect has to be done. Some research is being done in that direction, but not much. Yeah. And again, everything is going to be like in the form of AI applications. Yeah. So think always from these AI applications and AI workload. Okay. And cost is the most important factor. Yeah. So you cannot come up with any kind of solution maybe that is considering both sustainability and security, but if it is very costly, then nobody is going to use it, nobody is going to pay for it. Yeah. So always think in cost effective manner. Okay, another trend that I feel can be is hierarchical management of multi-cluster platforms. Yeah. So with increasing complexity, yeah, and technological advancements, so we can see like there are multi-cluster platforms. Yeah. Like in the phone, I saw you, there's a big cluster, there's little cluster, and there's GPU cluster. Yeah, 3 clusters are already there. So similarly, MediaTek, you may know, their processors also have 3 clusters. So multi-cluster architectures are coming into picture. Similarly for chiplets, I saw you, right, the chiplet 1, chiplet 2. One chiplet can be one processing element, or one chiplet can itself be a multi-core chip. Yeah, so then there are like each of the chiplets are a cluster. So these kind of things are going to come into picture, and they will require some kind of hierarchical management. Yeah. So where one of them can act as a local manager that can basically decide how the things are going to be managed. Okay. And then so one of them is like global manager, but then at each of the clusters there is a local manager. Yeah, it's managing locally, and then something is managed globally. Again, it's kind of the concept is like an organization. Yeah, like for IIT Guwahati, there is a director. Yeah, he's a global manager, but then there are a lot of departments, and the head of the departments are local manager. So they are managing. Yeah, but this global manager is not talking too much to the students of that department or the faculty of that department. He is talking mainly to the head of the department. So the head of department is local manager, and the director is the global manager. So similar kind of hierarchical management is needed into these kind of systems as well. Also, to kind of reduce the management complexity, a cluster can be divided into another subclusters, right? For example, like I said, head of the department, right? Sometimes if the department is big, there could be deputy head of the department, or head of education, head of research. So they can deal with different kind of things. Yeah. So again, if the platform is big, you can have subclusters. Again, these kind of things are already happening. Samsung Galaxy S10 mobile phone started this. So they had a cluster, and that cluster was divided into two subclusters. Okay, so that's going to help with the management. And finding the best hierarchical management policy is challenging. Yeah, if like so many things are there. Okay, I don't think we have time for this question. I was like, can you think of any other emerging trends? Yeah, so I talked few. Like it could be more and more side channel attacks. You need to consider security sustainability together, and hierarchical management is important. Yeah. Any other trends? I think don't worry, because we do not have time. Yeah, but you can think about it. Yeah, what can be there. So with this, I would like to acknowledge my many members of the group. I think not everybody is listed, because this research, if you remember, I saw something from 2010 or something. Yeah, so it's like 15 years. So there are many people involved. Thank you. Any questions? No? Yeah.
So instead of that, can we use any optimizer tool to sort that?
Yeah.
So how we decide that? Which one?
I think if you want to use any optimizer tool, the main task is how you fit your problem into that optimization. Yeah, it's like how you design the input to that. Even for the genetic algorithm, I said, right, you have to design the genes in a way it represents your problem. Yeah, so one of the gene is representing how the task is mapped on the core. A few genes are representing what will be the voltage frequency labels of the cores. So you can use other optimizer tools. Yeah, there are, like I said, tabu search, integer linear programming, all these are used. It's just they work nice, but they're for different purpose. Yeah, you need to feed your problem in a way they understand it. Yeah.
So we cannot this one will work better in this.
I think you need to evaluate. Yeah, so I think maybe you are saying which one is better, like genetic algorithm, tabu search, or maybe reinforcement learning, which one is better. So I think first of all, like you should think like yourself, which one, what is your situation, and which one will be better. Yeah, and then you will be left with some options. Yeah, and then you kind of try all of these and find the best from there. Yeah. Okay. Any more questions? Okay, if not, then it's lunchtime. Yeah, and this is my last lecture. I think from here Dr. Momita will take, and tomorrow Dr. John will have lecture. Yeah, on Friday I think you have some test. Yeah. Okay, good.